Hello students, let us start with 7th part of chapter 13 hydrocarbon. Methods of preparation of alkenes. Number 1, by partial reduction of alkynes. The catalytic hydrogenation of alkynes to alkenes occur faster than that of alkenes to form alkanes. Since alkynes show geometrical isomers, alkynes can be reduced to give cis or trans alkenes depending upon nature of catalyst used. For example, catalytic reduction of alkyne in presence of palladium supported over calcium carbonate or barium sulfate and partially poisoned by addition of lead carbonate, sulfur or quinoline, which is called Linder's catalyst, gives cis alkene. If alkynes are reduced with sodium in liquid ammonia, that is Birch reduction, trans alkenes are the major product. On the screen there are both type of reaction. Let us start with first reaction. Here we are with symmetrical alkyne CH3C triple bond CCH3 with dihydrogen and Linder's catalyst. It is reduced to double bond. Triple bond is reduced to double bond. In this case, both methyl group are on the adjacent side. So it is case of cis isomer. If we use catalyst sodium or liquid ammonia, then the methyl group will be on the opposite side and it is case of trans isomer. Number 2, from alkyl halide or haloalkanes. Alkyl halides on heating with a strong base such as sodium ethoxide or a concentrated alcoholic solution of potassium hydroxide undergo dehydrohalogenation to give alkenes. Now what is dehydrohalogenation? The process of removal of a molecule of halogen halide from a haloalkane to form an alkene is called dehydrohalogenation. Dehydrohalogenation is an example of elimination reaction. In this reaction, a hydrogen is removed from beta carbon and halogen from alpha carbon. Therefore, it is called beta elimination reaction. Third point, from vicinal dihalides or 1,2-dihaloalkanes. Dihalogen derivatives of alkenes in which the two halogen atoms are present on adjacent carbon atoms are called vicinal or 1,2-dihaloalkanes. Alkanes can be prepared by heating a suitable vicinal or 1,2-dihaloalkane with zinc dust in methanol or ethanol. Take this example. Here we are with the example 1,2-dibromoethane, that is BrCH2CH2Br. When treated with zinc dust, there will single bond is changed to double bond, means reduction. So it is CH2 double bond CH2 plus ZnBr2. With a different example, CH3 single bond CHBr, CHBr CH3 and zinc. It gives CH3CH double bond CH3 and ZnBr2. So what is dehalogenation? Now we are starting dehalogenation. The process of removal of molecule of halogen from a dihaloalkane to form an alkene is called dehalogenation. Even 1,1-dihaloalkanes or gem dihalides also undergo dehalogenation when heated with zinc dust in methanol. CH3CHBr2 when treated with zinc. Here is the case of 1,1-dibromoethane when treated with zinc. It gives CH2 double bond CH2 and ZnBr2. Now one more example, CH3, CH2, CHBr2 and zinc. It gives CH2 double bond CH2 and ZnBr2. Fourth one, from monohydric alcohols or alkanols by acidic dehydration. Monohydric alcohols or alkanols containing a beta hydrogen on heating with a mineral acid such as concentrated sulfuric acid or phosphoric acid on passing their vapors over heated alumina at 623 to 633 Kelvin eliminates a molecule of water to form alkenes. Since a water molecule is eliminated from the alcohol molecule in presence of an acid, this reaction is known as acidic dehydration of alcohols. For example, CH3CH2OH, it gives CH2 double bond CH2 and water in presence of alumina at 623-633 Kelvin. Now change the catalyst and temperature. If we use 95% sulfuric acid at 433 to 443 Kelvin, then it will also give ethene. Now again by changing the catalyst and change the reactant also. Now we are dealing with different alcohol, that is CH3, CHOH, CH3. Now OH has different position. It will give again alkene and no doubt number of carbon atom remain the same. Now fifth point is from potassium salts of saturated dicarboxylic acid. This is Kolb's electrolytic reaction. In fact, Kolb electrolytic reaction was in alkanes also. It was also done there. Now start with again here. CH2 single CO negative Na positive, taking the sodium carboxylate salt CH2CO negative Na positive. Upon electrolysis, it gives CH2CO negative, CH2CO negative with release of sodium ion. First start with sodium ion. Sodium ion at cathode, it gain 2 electron. It changes into sodium. When it absorbs water molecule, it gives sodium hydroxide. Metal when react, sodium metal when react with water, it gives its hydroxide and release of hydrogen gas. Now come back to your anion which is at anode. It release 2 electrons and give CH2 double bond CH2, that is ethene. So ethene is formed by Kolb's electrolytic reaction. Physical properties of alkenes. Number 1. Physical state, color, smell. The first 3 members of the family, that is ethene, propene and butene, are colorless gases. The next 14 members are liquid, while the others are solids. Ethene has pleasant smell. All other alkenes are colorless and odorless gases. Next point, solubility. They are insoluble in water but are fairly soluble in non-polar solvents such as benzene, petroleum, ether. Third point, boiling point. Their boiling point increases regularly with increase in molecular masses. The boiling point generally increases by 20 to 30 Kelvin for the addition of each CH2 group in the chain. Straight chain alkenes have higher boiling point than isomeric branch chain alkenes. Alkenes undergo electrophilic addition reactions. Alkenes are characterized by presence of what? Double bond and weak pi bond. That is, double bond means one sigma bond and one weak pi bond. The pi electrons form an electron cloud which lies above and below the plane of sigma bonded carbon atoms. These pi electrons are more exposed and hence are less tightly held between the two carbon atoms. Since the electrons are negatively charged particles, therefore the pi electron attract the electrophiles and repel nucleophiles. So, thank you.